let's continue thinking about stress. And why are we doing this? Well, oftentimes you're designing something, and designing something means you're picking out what you're going to use, what kind of material it is, and what size and shape is the material. Sometimes you have a structure that already exists, and you want to figure out how heavy a load could it take. You have a deck, could you put a hot tub on it, or something like that. Here's our stress formula. Stress is PSI, pounds per square inch. And you might recall, any time that you have an equation with 3 terms in it, you can use one of these handy triangles, the Mueller diagram. So you got a P over A, so we'll put the P on the top, the A on the bottom. We'll put the stress in the other side of the triangle. And these lines in the triangle tell you what to do. So this horizontal line tells you you divide by the thing in the top, divide by one of the things in the bottom. This vertical line tells you if you have 2 things side by side, you multiply them. And with your finger, you cover up the one you're looking for, the one you don't know, and then you see what order are the other 2 in. So for example, if you're trying to figure out force, you cover that one up. You're left with stress next to area. That tells you that your formula for finding force will be force is stress times area. It's just a handy shortcut. You don't have to use these triangles. You can just use good old algebra and rearrange the terms, but some people find these convenient. So when you rearrange the terms, or you use this triangle, you will wind up in these 3 different configurations of stress, force, and area. Last time we looked at this 1 by 1 bar, and we figured out that it had 100 psi in it. And then we looked at this 10 by 10 bar, and we figured out that just by increasing the size of that bar, we wound up with only 1 psi in it. Well, let's continue on. Let's think about this particular thing as a post. I don't know why I drew it on its side. I should have drawn it straight up and down. Oh well. It's a post. It has a 200-pound force pushing on it, and it's a 2 by 2 post. And let's figure out how big is the stress in it. Well, let's think about what are we looking for? What are we trying to find? Stress. And what are we given? What do we know? We know the force. There it tells us 200 pounds. And they don't tell us the area, but they tell us that it's 2 by 2, so we could figure out the area pretty quickly. 2 by 2 is 4. So the equation that we need is our good old stress equals force over area. All right, now we can do that. Stress is force over area. How big is the force? It's 200 pounds. How big is the area? It's 4 square inches. And so we find out, there are 50 psi of compressive stress in this post. Let's look at this one. I drew this one right vertically, like a post should be. So here's a post. It has a 3,600-pound weight sitting on top of it. The post is 6 by 6, and then it's sitting on a footing that's 60 by 60 to spread out the load. So let's figure out how big is the compressive stress in the post, and then we'll figure out how big is the stress in the footing. What do we know? What are we given? We are given the force. Here it is. The force is 3,600 pounds. And we're sort of given the area. We're given the 6 by 6 size, and we could quickly figure out that the area is, what is 6 by 6? 36. And so we're going to find the stress. and we'll use our good old stress equation. So in the post, 3,600 pounds of force divided by 36 square inches of area, 3,600 divided by 36, we have 100 psi of stress in the post. How about the footing? The footing is 60 by 60. What is 60 times 60? It is 3,600. So we still have 3,600 pounds of force sitting on top of it, but now it's distributed over 3,600 square inches. So under the footing, we have only 1 psi of stress. Same amount of force coming down, but it's spread over a bigger area. So each little square inch is feeling over only 1 pound. And so just to emphasize, there is a difference between force and stress. For example, in a skyscraper, let's say in New York City, I read about this example in the World Trade Center before it came down. So the engineer was talking about 1 million pounds of load coming down on a column, on a footing, on a pad. And you might think, oh, 1 million pounds, that's horrible. But if it's sitting on a footing that is 83 feet and change, on 83 1/3 feet on a side, well, 83 1/3 feet on a side, 83 times 83, gives you 1 million square inches. So even though you have this skyscraper and 1 million pounds of weight sitting on this post, you have only 1 psi of stress in this footing. Now, I grant you, you've got a big amount of stress in the post, but if you're just thinking about the footing, that load gets spread out quite a bit. Okay, let's think about another one. So here is a beam, big old beam. It's got 32 pounds of force, 32 pounds of load sitting on it. And it's divided among 2 posts. One post over here is 2 by 2. The other post on the right is 4 by 4. And we want to figure out how big is the stress in each post. So what do we know? Well, we know that there's 32 pounds of force coming down. We also know that it's split. Half of the force on one post, half of the force on the other post. So when we say we know the force, we should be thinking, well, we have 1,600 pounds over on one side and 1,600 pounds over on the other side. And then we could figure out the area of the small post and the big post, and from there we can figure out the stress. So we'll use our standard stress equals force over area. Stress is PSI. All right, so for the small post that's 2 by 2, we have half the load, so 1,600 pounds, sitting on that post. And that post, 2 by 2, is 4 square inches. So on that side, the small post must be feeling 400 psi, 400 pounds per square inch of compressive stress. How about in the big post? Think about what might you predict. With what you know so far, you might be thinking the stress is probably going to be lower in that bigger post. Let's see if that's the case. So it was 400 psi in the little one. Let's look at the big one. So it too has 1,600 pounds of load on it. It's got a 4 by 4, so an area of 16 square inches. Stress equals force over area, so 1,600 pounds per 16 square inches. Yep, we do wind up with lower stress. We wind up with 100 psi on this side. It was 400 on the little post. It's only 100 on the big post. Now let's go a little bit different direction. this is a steel bar, and we are told that the allowable stress in this bar is 22,000 psi. And this is a common thing to run into when you're designing something. They will tell you, well, you're allowed to have 22,000 psi of stress in this bar before it fails, before something bad happens. And it's a 2x2 bar. The question is, how big a load could we pull? How big a load could we have on it? So if we're looking for load, if we're looking for force, we're going to want to rearrange those terms. So we're looking for force. We know the stress, 22,000. We know the area, 4 square inches. What we're looking for is the allowable force. That's the P in our equation. So that's the one we'll cover up. And that means that our equation is going to be stress times area. So force is stress times area. Let's do that. So force is stress times area. Our stress is 22,000 psi. Our area of our 2x2 bar is 4 square inches. 22,000 times 4 gives us 88,000 pounds. That is the allowable load for this steel bar. And if you have been in a math class, you probably have done some what they call unit analysis, where, yeah, you got these numbers and things, but how do you know that you want to put pounds out here? Other than you're looking for force, so it's got to be pounds. But how do you get there? So just quickly, let's think about that. I've written the PSI this way: 22,000 pounds per square inch, PSI, times 4 square inches. So we've got square inches on top and square inches on the bottom. The square inches cancel out, and the only unit we are left with is pounds. So the 88,000 has got to be pounds.